Okay, so what do we mean by that? I got the computer up and running here. So a function can approach infinity or negative infinity as x approaches a number. What would a picture of that look like? Well, when I say a function can approach, what I'm talking about is the y value. Okay? So let's draw some pictures of this. Here's the first picture I'm thinking of. So somebody give me any number. 3. Okay, so let's say that we're talking about x is approaching 3, and the y is getting infinite. So one picture would look like this. This is one possible picture. As you get near 3, the y is becoming infinite. Here's another one. Here's x equals 3 again. As x is getting closer to 3, the y is approaching negative infinity. See? Or here's a third picture of this situation. Maybe you're coming at 3, but you're actually coming from the other side of 3. So it looks more like this. See? So you're coming from the right. Or maybe even you're coming from the right, but it's going down to negative infinity. See? Or maybe it's coming from both sides of 3. You could have a picture like this. And as you come towards 3 from both sides, the graph is going up to infinity. Or maybe you're coming from both sides of 3, and the graph is going down like this. These are all examples of vertical asymptote behavior. And the last two pictures, there's 8 pictures total, is you're near 3, but on the left side it's going up to infinity, and on the right side it's going down to negative infinity. So we have opposite behaviors, one on each side. And we can flip that thing upside down and have it where it's going down on the left and up on the right. So this is my 8th diagram. 1, 2, 3. Imagine if it was dropping on this side and rising on this side. So all of these can be given limit statements, which is a really good thing to practice right now. So what I'd like to do is just go through and just write all the limit statements. Okay? So the first one I'll start with is the limit as x approaches 3 from the left of f of x is infinity. That is the appropriate limit statement to write for this. All right, so now I'm going to call on you, and you can help me write these others. Okay? So let's go on to the next picture. That's this one. Limit as x goes to what of f of x is what. So let's not shout them out, but I'll call on you. So let's have, why don't we do Carly? How would you write this one? As x goes to what? Plus or minus? Okay, what does that mean, that little minus? Okay, yeah, we're coming from the left side. We're going this way. Good, so we're on the left of 3. Good, and then the answer is what? Right, the limit is negative infinity. Good. Okay, let's fill in this next one. So we have limit as, and let's go to Jessica, limit as x goes to what?
2, 3.
From which side? Good, so we use a plus. Of f of x is? Okay, now notice this one's actually shooting upwards. Oh, sorry. Yeah, we're on this one. So this one's positive infinity. So you're saying that this one's negative infinity. Why is this one negative infinity? Right, so we're on the right side of 3. The graph is going down. Negative infinity. All right, good. Let's go to the next row here. These ones are double-sided. So how does that change what we're planning to write? So Jordan, what changes now as we begin to write these statements? What changes?
Do you not have to put a sign because you can just put 3?
Yeah. So if you see a double-sided problem, you're supposed to think about both sides. You don't really have a choice. You don't know which side's more important. So we drop the whole superscript idea, and we just go with x goes to 3. All right. What is the answer to this one? Correct. Why is it infinity?
Because the arrows are going.
Yes, she said it correctly. That both arrows are going upward. That's why the answer is infinity. So the next answer would be, so what's my next one here, Lynn? Limit as x goes what?
X goes to 3,
Uh-huh.
and then the f of x equals to infinity.
Right. Notice we're not using the plus or minus on that 3. Okay, now let's go to the next one. These next two are sort of special cases. So I'll change colors. If you were asked what is the limit as x goes to 3 for this diagram, what would you go with, Catherine?
You do the limit as x approaches 3 from the left, f of x equals infinity,
Okay.
and then the limit of as x approaches 3 from the right, f of x is negative infinity.
Okay. And the fact that they are different answers.
Undefined.
But we don't say undefined. We have another name for it. Blake? No? That's 0 over 0, or there are some others, but yeah. Yeah, we say does not exist. Okay? Does not exist. And that's actually true for both of these because the double-sided behavior is different. It's like one behavior is on one side and there's different behavior on the other side, so you can't say with certainty what the behavior is near 3. There's a difference on which side. So the double-sided limits, you got to make sure that both sides look the same. Otherwise, you just put D and E, which means does not exist. And I just want to say this here real quick. The word limit doesn't mean in math what it means in English. Okay? If you hear someone say, the sky's the limit, what they mean is there is no limit. Which they mean infinity is possible. It's like impossible is nothing, Adidas. Adidas has this slogan, impossible is nothing. It's a great slogan, but that you might think, oh, that means no limit, you know. There's no limit to how great something can be, or how great you can be, or whatever. Okay? But that's not what no limit means in math. No limit in math means there's no agreed upon behavior. That's what it means. Or there's no one decisive behavior. There's nothing really to do with infinity. In fact, the limit can be infinity. That doesn't even make sense. How can the limit be infinity? That's the same thing as saying there is no limit. But we don't say no limit here. We say infinity. We say negative infinity here. This is when we say DNA, it's whenever there's a disagreement. Okay? You can just memorize that if you want. All right. So all of these, though, are called what? Vertical asymptotes. Right. Vertical asymptotes. Now let's talk about horizontal. Okay, so horizontal asymptotes is different. Here's our second reminder. Also, recall, a function can approach a number as x goes to positive or negative infinity. This is sort of backwards from what I had said a minute ago. I said a minute ago that the function can approach positive or negative infinity as x approaches a number. This is different. Now the function is approaching a number, and the x is approaching infinity. It's flipped around. So what does this mean? This means if you go way, way out on the right, a graph might be rising towards 5. See? So the x is becoming infinite. The y is becoming a number. And we saw several pictures for this too. You can have it coming from underneath like this. You can have it coming from above, down onto the line y equals 5. You can have a drawing where y equals 5 is a horizontal asymptote, and the function's actually oscillating onto it, wiggling its way onto that line. Remember we talked about that. But in all three of these pictures, we would write the same conclusion. the limit as x goes to infinity of f of x is 5. It applies to all three pictures. Because all it's saying is, in all three of these graphs, as we go out to the right, y is getting closer and closer to 5. Whether it's coming from 4.9 to 4.99 to 4.999, or whether it's coming from 5.1 down to 5.01 down to 5.001, or whether it's doing 4.9, 5.1, 4.99, 5.01, 4.999, 5.001. In all those cases, the value that's being approached is 5.0. 3 drawings. That's just for the right end behavior. You can also have a similar thing happening out on the left. So you can also draw all these same pictures again. This time, let's draw a line here to separate it from the last set of examples. How about a drawing like this, where this is line y equals -2, and the graph is coming down onto it. Or down from underneath up to it, see? Or wiggling onto it like that. You would write the same conclusion on all three of these cases. The limit as x goes which way? Yeah, we're way out on the left. X is going to -infinity. The function has a limit of what? -2. That's true for this picture, that's true for this picture, that's true for this picture. They're all the same. In fact, one graph can have two different behaviors. It can have a behavior out on the right and a behavior way out on the left that are different. How in the world is that possible? Well, let's look back at all the flashcards you've made. There is actually one flashcard you made that has 2 horizontal asymptotes. Do you remember it? You made a flashcard for me, and it had 2 horizontal dashed lines. Do you remember which one it was? What's that? Yeah, it looked like this. I'll draw it, see if you can remember what it was. Which graph was this? Inverse tan. Yeah, arctan or inverse tan. Inverse tan is a classic example of what we're talking about right now. It has 2 horizontal asymptotes. This one is at y equals pi over 2, which means y equals 1.57. And then there's another one down here at y equals -pi over 2. That too is a value of y. And what's going on is as you go to the right, this graph is climbing towards that line and ultimately trying to become that line. And that's happening out on the left as well with a different line. So what you would write for this, see if you can write the 2 limit statements for me, okay? See if you can fill this one in. What is the limit as x goes to infinity? And see if you can write what the limit is as x goes to -infinity. See if you can fill these in for me, because that shows that you understand what I'm saying. And yes, this graph has 2 horizontal asymptotes defined by these 2 behaviors. Okay, so see if you can fill those in. Hopefully you understand what they mean and how to pronounce them. So Amina, what is the red answer? Pi over 2. And what's the blue one? -pi over 2, right. Because as you go out to the right, the graph is rising towards pi over 2. As you go way out to the left, the graph is descending upon -pi over 2. So there's 2 different behaviors. Yeah. Okay. So that's how you actually find horizontal asymptotes. Let's say someone gave you a cookie-looking function like this, and they said find the AJs, find the horizontal asymptotes, and they gave you this maybe. This is kind of like the one I did last week. What you would want to do is study the x values, study the y values when x is extremely large, and when x is extremely negative. So like you would play around with the idea, what if x was huge, you know? So you'd write that like this mathematically, and you would think about it, and we talked about spit in the ocean. What happens when you spit in the ocean? Pretty much nothing, right? Technically, according to the conservation of mass and energy, you did increase the volume of the ocean a little bit. I'm sure something else evaporated somewhere else, right? Maybe more than you spit in. But the point is, you can look at 2 to the x, and you can look at 3, and you can ask if x was 1,000,000, which one really is the significant term? Obviously 2 to the x. So we talked about this. 2 to the millionth is so much further from 0. It's like the 3 doesn't even matter anymore. And the same thing happens on the bottom. There are 2 terms. The first one is the ocean. The other one is like spit in the ocean. And so you can end up with basically 3 times 2 to the x down here. And you've basically turned this into a really simple problem, because what happens to the 2 to the x? It cancels out. And you end up getting basically what happens to 1/3 when x gets big? It stays. It's saying what happens to 1/3 when x becomes very large? There's no x. 1/3 will always remain 1/3 no matter what x does. So this goes to 1/3. What this means is that we might not be able to sketch this graph very well with our current level of skill, but we know this. Way out on this side, see, there's a line y equals 1/3, and this graph is either climbing towards it, descending onto it, or wiggling onto it. That's what it means. Now let's try the left side to understand that. So if you try to do a left limit, you would just use a negative infinity. Be careful here. Do not assume that 2 to the x is always your ocean. Technically, if you plug in a negative 1,000,000, you're going to have 2 to the minus 1,000,000 minus 3. You know what that's really close to? Negative 3. That is so small now, because you're plugging in negative 1,000,000, negative 1,000,000, negative Google. That term right there vanishes. Right? 2 to the minus 1,000,000 means 1 over 2 to the 1,000,000. That's 0. So what happened was the ocean became the negative 3, and that's now spit. And the same thing happens downstairs. The 5 is the ocean, the 3 times 2 to the x is spit. So we change our mind about who's the ocean, and we go with these as our oceans, and we have a different conclusion now. Now we would conclude with this question, what happens to negative 3/5 when x goes really negative? Nothing. So what does that mean graphically? That means if you're out on the left, this line is approach. This is the line of approach. You know, you could say that. This is like the destination of the graph. Either it's descending onto it, rising toward it, or wiggling onto it. So you can have 2 different behaviors. This doesn't happen very often in our textbook problems, but it happens all the time next year. And it happened on your tan inverse graph, so we shouldn't have any gaps in understanding. Okay, if you use the textbook to learn HAs, you will miss out on this fact, and then you'll have a hard time relearning it next year. Now you've seen that this is really a limit question, not a memorization thing like our book treats it as. Okay, and then the last thing is the slant asymptote. Slant asymptote. Okay? Slant or oblique, and this is actually the easiest one of the 3 to study, and it doesn't even show up on every problem. So, first thing is, this only happens when you have like x to the n plus 1 up here, and on the bottom, you have x to the n. For example, if you have f of x equals 3x to the 4th minus 2x cubed plus 5 over 6x cubed minus 4x minus 6. If you see this problem, you can be sure right away that there is a slant asymptote, and here's why. Notice that the top has degree 4, and the bottom has degree 3. That's a huge clue. What that means is, if you look at the 2 ocean terms, right, that's this guy and this guy, you'll see that this does not really reduce to a number. It reduces to 1/2 x, which is a line, see, with slope f. So what it means here is, if you see that the oceans on top and bottom are producing something like mx, so this would give you 1/2 x. Here's what it means graphically, okay? This is a graph, some crazy graph, and it is approaching either, it's approaching some line with slope half. So it's approaching 1/2 x plus 1, or maybe it's approaching the line 1/2 x plus 4, or maybe it's 1/2 x minus 3. It's approaching some sloped half line, and you can get that line by long division, which you guys are really good at. So I'll just do it real quick. You would take this, and you run a synthetic long division on it. Sorry to keep you here. If you have to go, you have to go. But I was just going to finish this example real quick, since we're really close. Remember to put in like a 0x squared and a 0x. But first you divide this in, you get 1/2 x, like I promised. Multiplying this, you get 3x to the 4th minus 2x squared. So I'll have to line this up with a 0x cubed here, minus 2x squared. And there's also a minus 3x. And then when you subtract this, you'll see it comes out to negative 2x cubed plus 2x squared plus 3x. See? And you do one more division. So what do you multiply 6x cubed by to get negative 2x cubed? Well, that's minus 1/3 x, minus 1/3. So that becomes your next term right here. That's your line right there. Now there is a remainder term. Okay, there's another term here, but it doesn't matter because it's something over x, and it's going to vanish when x gets big. So this part will just vanish away, and there's your mx plus b. That's your slant asymptote. Okay, so you can basically finally conclude that this green line we drew earlier, I'm erasing it now, but we had said that there's going to be a slant asymptote at 1/3 x plus something. It turns out it's 1/3 x plus negative 1/3. This is your slant asymptote. Passes through, obviously, negative 1/3, which is right about here. And the graph, even if we can't draw it completely, we know it sort of follows it, either from above or below, out at extreme values of x. All right? Okay. Now, one more comment about these before we move on. Some functions have different behaviors on the right versus the left, but a problem that has a polynomial numerator and a polynomial denominator is called a rational function. So since these are both polynomials, that means they're basically no square root, x's, or sines or cosines or anything. It's just x's and x squareds and x cubes and constants like these. And because all the coefficients are real numbers, 3, negative 2, 5, 6, negative 4, negative 6, and because all the powers are whole numbers, right, 4, 3, stuff like that, we can basically say that this is called a rational function. And you can trust that on a rational function, the behavior on the left and the right are similar. So you don't have like one behavior on the right, one behavior on the left. They're both going to approach that same green line, is what I'm saying. It is possible to have a function with two horizontal asymptotes. Classic example of that is what we talked about earlier, arctangent. So arctangent actually has, you drew a flash curve for it, it actually has two horizontal asymptotes. It's got y equals pi over 2 for the right-hand behavior and y equals negative pi over 2 for the left-hand behavior. So you can have two horizontals. You can also just have one horizontal, right? A classic example of that is your e to the x curve. E to the x looks like this, right? E to the x. It has a right-hand behavior that tends towards 0. I'm sorry, left-hand behavior that tends towards 0. That's for this side. But for the right side, it actually shoots up to infinity, and it's almost like this asymptote plays no rollover on this side, and that's kind of the way it is. Okay, is it possible to have a horizontal and a slant? And the answer is if you're willing to draw something that's not a function. So for example, if you drew a horizontal and a slant, you could potentially draw a curve here, either like this, blue, or like this, red, or like this, purple. But the problem is, these are not functions. Whether you go with the blue graph, or the red graph, or the purple graph, there are spots where it doesn't pass the vertical line test. So one of my questions on the worksheet was, can a function have both a slant and a horizontal? And the answer is no. Not really. Unless it's a piecewise function, then you can kind of make anything happen. Okay? So there you have it. Typically the answer is no. And on a rational function, polynomial top and bottom, no way.